Okay, so the topics we are going to see in this chapter. You can also call as finite state machine. The another name of this one is finite state machine. We call FSM or FA. What does this finite automata does? It represents which language? It is a machine represents a regular language. Regular language, you can also call it as regular set, because language another name is set. Finite automata also called as finite machine, which represents a regular language. What is the job of this finite automata? Very simple. We design a theoretical model. This is a theoretical model. This machine always represents a language, right? Represents some language. If you give any string to this machine, what does this W? Input. Then this machine automatically does some job. If the string belongs to L, this finite automata halts at final state. If the string not belongs to L, the finite automata halts at non-final. So if the W belongs to L, we call it as valid member of the language. If W not in L, that means invalid member of the L. So we run a string on the machine automatically halts some state. That state is, if it is final, then the string is valid. If the state is non-final, the string is invalid. So what is final state? What is non-final state? We are going to look at in the configuration. Okay, with the help of an example. If you look at regular expression is some kind of expression, and that represents also a regular language using 4 operators. Okay, are you able to differentiate? When you write a regular expression, means you are representing a regular. When you are designing a finite automata, it also represents a regular language. Okay, so you can use either regular expression or finite automata for understanding. Right, are we ready? Starts with the configuration. Look at the theoretical model of the finite automata. You can see this configuration. This finite automata comprises of 5 parameters. They are Q, sigma, delta, Q naught, and F. So what is Q here? Q is set of states. If you look at in this machine, Q nothing but 1, 2. There are 2 states which represent with the circle in the graph. And sigma is set of symbols also called as alphabet. The sigma is equal to here A comma B. Delta is a transition function to represent type of finite automata, DFA or NFA. We'll see that. What is delta for? And Q naught is a start state also called as initial state. And F is, here Q naught is what? The 1. Here Q naught, you can call it as a 1. Every machine should have only one final state. And F is set of finals. Sometimes you don't see the finals, then F should be empty. So here F is nothing but only 2. And this F could be empty or only one state or 2 states, whatever you require. So set of final states is nothing but F. And these are the 5 parameters that you should understand for every machine. And here, what is delta? Delta is for a deterministic finite automata, Q cross sigma, Cartesian product of Q and sigma, and codomain is the Q. When it is NFA, Q cross sigma, that maps to 2 power Q if you don't want epsilon. If you want epsilon, then you can also write Q cross sigma along with epsilon, you can map to 2 power Q. So one is without epsilon, other is with epsilon transitions. So this is how you can define what is finite automata. If you look at this machine, it is a control, right? This is called as initial state. We will work on it. But here, what is one called as initial state, Q naught? That's why this arrow always you see for initial state. And only one initial state here. And there could be 0 or more finals. If no finals also, it is a finite automata, right? Double circle represent final here. So 2 is final here. Machine may contain 0 or more finals. Right. What are the transitions here you see? Based on this definition, delta of 1 comma A, what will you have? It goes to 2. And from 1 by reading B, it is self loop. 2 comma A is 1 and 2 comma B, which is 2. So there are 4 transitions which are defined based on this definition, right? For this definition, you should write different way. Q cross sigma will work, but 2 power Q means here subset should be there instead of only the element. Okay. We'll see the difference between these two, DF and NFA. So let's work on DFA versus NFA. How they are different from one to other. What is the full form of DFA? What is the full form of DFA? Deterministic finite automata. This one non-deterministic. If you look at the first definition, that is, it depends on a transition function. Domain is q cross sigma, that is q, and this is the definition of transition function, correct? Whereas in a definition, q cross sigma, epsilon is optional. If you want it, you can take it. That maps to 2 power q. You can write sigma epsilon or sigma union epsilon, both are same. What is the meaning of this DFA? This is a q cross sigma maps to q, which says that if you look at the graph, is this DFA or not? If you look at this, it is DFA. The reason is, if you assume this is a 1 and 2, 1 comma A, 1 comma B, 2 comma A, 2 comma B, you have exactly one transition. Yes or no? From every state, for every input symbol in the sigma, you will have exactly one state. The definition exactly matching here. When you look at the NFA, you can have the same machine or you can also have a different machine. You can see here. Now here, if I say what is 1 comma A, you don't get a state, you will get subsets. Like either 1 or 2 it can live. If I ask delta 1 comma B, you don't get nothing. You don't get anything here. You get nothing. 2 comma A, you get nothing. 2 comma B, you get only 2. So when you look at these transitions, that is exactly matching Q cross sigma that maps to Q. Whatever you take that belongs to Q, whatever you take that belongs to sigma, whatever you take here that belongs to Q. Here it matches with the Q cross sigma maps to 2 power Q. Whatever you take it belongs to Q, belongs to sigma. This R belongs to 2 power Q. Okay, this R belongs to Q because it's the only one state. Here 0 states possible, 2 states possible, 1 state possible. So 0 or more states possible, that is a 2 power q. So this is the main nature of the non-deterministic motion. And if you look at this, even every DFA, it also belongs to 2 power q if you have only one element, right? So every DFA is also NFA, but NFA need not be DFA. The difference between these two is all the a transition that you write in DFA, you can take them as an NFA, but in NFA, these transitions never present in DFA, and these transitions never present in DFA because here exactly one state should be there, but here 2, here 0, here 0. This can come under DFA because from 2 by reading B it goes to only one state. That's correct. Okay. So what is the difference between DFA and NFA by looking at this observation? Go ahead. Final states are not required, Kiran. Everyone, we don't need a final states. One initial state is there. Final states can be 0. Everybody, do you require final state in the machine? Not required. That's why F is, we don't say final states, we say set. F is a set. It could be empty set or it could be a set which has only one state as a final. F is a set of finals. This set has finals. This set can be empty or non-empty. Okay. First, that's why focus on definitions. Do not worry about how to construct now. Learn all basics properly. What are those 5 parameters about? Okay. You can just look at who is DFA or not. Assume sigma is A comma B. Okay, do not assume anything else now. Out of these two, which are DFAs? Which are NFAs? Is this a DFA? This is not DFA, correct? What is it, NFA? Yes. Anything you see here, it is NFA. Everything here is NFA only. In NFA, anything is possible. Any number of transitions you can have. But the problem is DFA or not. From this state, by reading A, only one transition. So it's nothing but two different transitions. We write a comma to separate them. It is a DFA. In this one, for A, one transition, for B, one transition, for A, one transition, for B, also one transition, it is a DFA. It is also DFA. And why this is not a DFA? Because from this state, the transitions are missing. So if it is a DFA, from every state, you will have a transition for every transition, every input. What is the meaning of this one? This one means a set which can, it is set of all subsets. That subset may be empty, may contain one state, may contain two states, right? So if it is empty set as a subset, right, empty set, then that means no transition for that input symbol. If the set has only one element, exactly one transition. If the set has two elements, that has two transitions. Okay. Just try a few more. Sigma is same. Sigma is A comma B. Do not assume anything else. Go ahead. Which is DFA, which is NFA? Is it DFA? No, it is not a DFA because A and B transitions are missing. But is it NFA? Yes, it is NFA. What about this? From this A and B one transition, from this A is one transition, but B is not having, so it is not a DFA. But it is NFA. This one, from this state, for A one transition, for B one transition, for A one, for B one, and don't look at there is a path or not, or you don't worry. Is there any final or not? Don't worry about it. From every state, for every input symbol, you have exactly one transition. It is a DFA. Every DFA, you should know that it is also NFA. And here, from this state, for A, you have a two transition. One goes here, one goes here. And this never comes under DFA. But it is NFA. Here, remember, every DFA that you are looking at is also NFA. But NFA that you see in general may or may not be DFA. If you look at DFA definition, Q cross sigma maps to Q. Right? It doesn't matter how many finals. But what is the definition of this? From every state, for every input symbol, you will see one transition that goes to next state. So this Q represent every state. This sigma belongs to every input symbol. This represent one transition to the next state. And here Q cross sigma maps to 2 power Q or epsilon, include epsilon or is your choice. Here from every state, for every input, for every input symbol, you will be having 0 or more transitions. Sometimes no input symbol also you may have a transition. For every input symbol or no input symbol is your choice, because this epsilon demands without input also you can change the state. Okay, I'm just leaving epsilon. Because of this reason, you will see, you take any string, we'll check it how to do that. For every input string, this motion will have only one path. Exactly one path will be there. That may go to final or that may go to non-final. Same question that you read here. For every input string, you will see 0 or more paths. The reason is non-deterministic motion. The reason is non-deterministic motion. Here, if you take valid string, in valid string, both will have only one path. But valid string will have one path that halts at here also one path exists. Here for valid string, at least one path will be there. That should halt at final. Invalid string, zero or more paths, but every path will halt at non-final. Here any kind of string, one path exists. Here valid string, at least one path. Invalid string, either path will exist or no path will exist. If you have a path, more paths may exist. That all of them should halt at non-final for invalid string. In case if you want to know the definition clearly, if I give a string W, this DFA, assume that accepting a language L, here if valid string means belongs to L, exactly one path that halts at, exactly one path exists, and that halts at final. Whereas string not in L, here also exactly one path that halts at non-final. That's about DFA. When you come to NFA, definition slightly changes. If the string belongs to L, at least one path you will see that halts at final state. Remaining might be halting at non-final, but at least one path you will see that should halt at final. The string not in L, you will see 0 paths. There is no path exist. If you have a path, all paths halts at non-final. Okay. Example I can show you. You can see epsilon, all the strings should start with 1, right? Every string where it starts, state 1 only. Epsilon also starts from 1, but from 1, epsilon means don't read anything. Where will you halt? You will halt at 1 only. And A, it will start with 1. After reading A, it will halt at 1. B, it will start with 1, but after reading B, it will halt at 2. So any string, for any string, if the machine halts at final, then that string is valid. Now epsilon it halts at 1, so it is invalid. For A it halts at 1, the last state we say it is halting state. And 2 is the final. For B it halts at final, so B is the valid string. Similarly, you can read double E, where it halts, it starts from 1, it halts at 1 only, correct? 1 on A, 1, 1 on A, 1. So double A is invalid. AB, it's going to halt at 2. So this is a valid string. Similarly, if any string halting at final, you will have exactly one path. Even halting at non-final, you will have exactly one path. So whether it is halting at final or non-final, you will have only one path. Whereas in NFA, you can see epsilon, it should start with 1 and also at 1. A, it should start with 1. 1 on A, only one choice, that is 1. And B, there are two choices. One, it can go to 1 itself, or it can go to 2 also. Now tell me, is it valid string or invalid string? Here definition is at least one path should go to final. Out of many paths, is there any path goes to final on B? Yes. Look at this path. Don't look at this path, because our target is to reach final. Okay. And that is the reason B is valid, because this path also at final. And it is altogether non-final. Only one path is there. Only one path is there. And double A, invalid. AB, you can see AB is valid string. So any string which halts at final with at least one path, that is a valid string. In case if you don't have any path, of course you have a path here. In case if you don't have any path for any string, then you can say invalid without waiting, without understanding further. Now let's work on the finite automata representations. there is DFA, NFA, anybody will have some representations. You should aware of them. The finite automata need not look like a graph. It can be, table. It can be set. It can be written in English. So finite automata can have different representations. One representation just now we have seen. We are very comfortable with that. That is graph. Right. Second is a table. Third, you can write like set or function. In a graph, we have seen if you see this, the one is called as initial state, that arrow and circle that represent initial state. And when you don't have the double circle, single circle is always non-final. Here one is non-final because you don't have a double circle. If you have a double circle, that is final. And transition we represent like this, arrow and then some input. This is called as transition on A. Now table, you can see 1 and 2 are states. Initial state we can represent arrow, but final state either you can use circle or you can use even star 2, is your choice. You can use any one of them. Okay, either circle 2 or star 2. Input will represent as a column. 1 on A, you can see that goes to 2. 1 on B, it goes to 1 itself. And 2 on A, it goes to 2. 2 on B, it goes to 1. And now you can see Q cross sigma that maps to Q, the one of the element in the Q. Here, the arrow represents, like this is initial state. And you can use circle 2 or star 2 that represent final state. If you don't have the finals, don't write a circle or star. Okay. If you look at the table, whatever you write here is belongs to Q. Here belongs to sigma, and here belongs to Q. Q cross sigma that maps to Q. Correct? So every entry 1 on A 2. So this belongs to Q, belongs to sigma, belongs to Q. The definition you know it. For DFA, Q cross sigma maps to Q. For NFA, slightly different. I'm only drawing for DFA representation. Same notations also applicable for NFA. But table and graph looks different a little bit. Now set representations, finite automata or DFA, let's say Q sigma delta Q naught F. We know that. So these things you can represent with what you want. Q is what? 1 comma 2. Sigma is A comma B. Delta you are writing down. And Q naught is initial state 1. And final states only 2. To understand, this is F, Q, sigma, sorry. What I am doing. This is Q, sigma, delta, this is a Q naught, and this is F. And what is delta? We can write here. Delta, you can represent using individual mappings like 1 comma A 2, 1 comma B 1, 2 comma A 2, 2 comma B 1. You can write individual mappings, or you can write this whole thing you can represent with one set also. Delta is equal to the set, and each set you have a mapping from domain to codomain. Like you have 1 comma A that maps to 2, right? And similarly 1 comma B that maps to 1. 2 comma A that maps to 2. 2 comma B that maps to 1. Sorry, it's a comma. Just look at that parenthesis carefully. One parenthesis and other parenthesis I convert to brackets to understand. So domain and codomain element. Domain and how do you map to codomain? Domain and codomain. Domain and total pair. So total 4 mappings are there, 4 transitions you will see in the DFA. Able to understand all the kinds of notations in the exam, whether they give table or graph or set or function notation, you should understand. Any doubt so far? All theoretical concepts, we are trying to understand how a finite automata can be represented, can be understood with a lot of theoretical definitions. Can you revise all the points for a few minutes? Just go to the, take 5 minutes gap, look at what we have done so far. We've not started, but we just started, had theoretical concepts of both finite automata, DF and NFA. So let's start understanding both DF and NFA. So I'll explain how we design, how do we understand the given finite automata. Okay, have you revised all the concepts? Can we go? Okay, I'll give a machine. First tell me, is it DFA or NFA? First tell me, is it DFA or NFA? Answer it carefully. If it is DFA, it is also NFA. Why do you say only DFA? Okay. If it is DFA, it is also NFA. So you should say both DFA and NFA. Because this machine satisfies both the definitions, DFA as well as NFA. DFA says that for every input exactly one transition, for right from every state. NFA says that keep anything. So keep anything is also covered, having one transition also covered is in anything. Are you able to understand? This is the DFA, so NFA too. Every DFA in the world is NFA. Every DFA is in the world is NFA. No doubt it is a DFA, but also NFA. Correct? And remember, I saw a lot of people, they do mistakes. How many transitions here? How many transitions? Go ahead. In this motion, how many transitions? 4. Edges only 2, but there are 4 transitions. You can also design another way, like instead of A comma B, you can also write A and B separately. And instead of A comma B, A separately, B separately. Both are same only. Correct? Either you can draw with 4 edges or 2 edges, but you have how many transitions? 4 transitions. Got it? Edges and transitions, you no need to see the same. 2 edges but 4 transitions. 4 edges, 4 transitions. So if both are coming to the same state, so instead of having 2 edges, you can have a 1 edge. You can write it 2 input symbols there. Okay. 4. It is DFA? Yes, it is DFA. So definitely it also NFA. And to understand DFA, NFA, you can see the definition. Delta says that Q cross sigma that maps to Q. Q cross sigma, that means 1 comma A, 1 comma B, 2 comma A, 2 comma B. Q means only 1, 2. 1 comma A, that goes to 2. And 1 comma B also goes to 2. 2 comma A goes to 1. 2 comma B goes to 1. This is what DFA definition. And NFA, even you want epsilon, you can keep it. That's your choice. If you want epsilon, also you can take it. Like 1 comma A, 1 comma B, 1 comma epsilon, 2 comma A, 2 comma B, 2 comma epsilon. And 2 power Q means all the subsets. Empty set, only 1, only 2, and both. So what are the transitions you have? 1 comma A, you have, you can take 1 and 2. 1 comma A goes to 2. 1 comma B also. 1 comma epsilon, no transition. 2 comma A, 2 comma B, and 2 comma epsilon, you don't have a transition at all. So you will have this one, empty set. And it satisfies NFA as well as DFA. That is the reason every DFA is what? NFA. Everybody able to understand the statement? Why we call every DFA is NFA? You can prove why it is NFA. Only NFAs need not be DFAs. Yeah, please respond. Done. Now I'm going to draw the diagram. Tell me is it DFA or not, then we will understand what it does. Okay, first one, assume sigma is A comma B. Tell me this machine is DFA or NFA. Only one state is there, no final. Is it DFA or NFA? Is it satisfying the definition of DFA or NFA? It is NFA. Everybody understood? From every state, for every input symbol, exactly one transition says DFA, but there is no transition for the state. So it is not a DFA. But every machine that you see, it's NFA. We don't demand how many transitions. It is only NFA, but DFA, no. Correct? Now, can you tell me what is the language accepted by this machine? Accepted by this machine. First important point is going to happen in this question. Can you see any final state here? If you don't have a final state, what is the language accepted by this machine? Nothing. There is no string. Even epsilon can't accept here, right? If whether it is DFA or NFA, if it is not having final state, it should accept nothing. Correct? Nothing means empty language. It should accept nothing. No string is accepted here. Even I draw it sigma assume a comma b only. Okay. And tell me, is it NFA or not, DFA or not? And what is the language? Go. So it is DFA, so NFA. What is the language? Check it. So you have 2, 3, 4. Find out what they do. Yeah, it is also pi. Second is also pi because no final state. When there is no final state, the language is always empty. Yes, Kiran, right. Yeah, great. L is equal to a plus b whole star. Last one. Correct. Perfect. Why we call NFA? Because you cannot prove, you are not able to prove every input symbol there is a transition, exactly one, right? It is NFA but not DFA. Now, how do you know the language is having only epsilon? This is a pi, right? Here only epsilon, because from this state, if you don't read anything, you will halt there. That means you are accepting epsilon. But in this, when you don't read anything, you will halt there only, but it is not a final. So when there is initial state is non-final, epsilon is not in the language. Initial state is the final, then epsilon definitely in the language. And fourth one, it is DFA because for A one transition, for B also one transition, and every DFA is NFA. An initial state is already final, and every transition you will be here, so it is going to accept everything in the world which is sigma star. Also, you can write A plus B whole star. What are interesting points here? Look at if you take just like you have one state only, right? You have a state 1, let's say, and for A and B, for A and B, how many choices you have here? 2 choices. Transition may be there, may not be there. If it is there, it will go to 1. If it is not there, it will go to empty set. Here also 2 choices. Total, how many DFS that you can design? As you know, initial is the 1. Total 4 machines. 2 into 2, how many? 4 machines you can build without any finals. Without any finals, remember. Got it? When there is no transition, it looks like this. Only transition is there for A, but not here. It goes to empty, it goes to A. If it is goes to only B, here empty, then it looks like this. If you have a transition to both A and B, you will have final machine. So total 4 different fundamentals that you can design. One is the initial and there is no final, correct? With 1 as initial and no final state. Here look at all of them are doing the same job. They accept which language? Here also language is empty. Here also language is empty. Here also language is empty. And now somebody can come up with 2 states also. This is also fine. It is also accepting the language is empty. Yes or no? And that is also NFA. And now I'm asking the question, if I don't have the number of states restrictions, how many NFAs are there for the language empty? How many NFAs in the world are there which accepts empty? Go ahead. Question 2. How many minimum NFAs are there which accepts pi? Minimum in the sense the machine which has less number of states. Here if you take all of them, these are having 1 state, but this is having 2 states. Even though it accepts empty, but that should not be counted in the minimum NFAs. Only with 1 state you should count, because 1 state is already accepting the given language, empty language. What is your answer? How many NFAs are there which accepts pi? Infinite NFAs you can design. 1 state, 2 state, 3 state, like that. Infinite NFAs. How many minimum NFAs are there which accepts pi? These are the only 4 machines over the sigma is equal to A comma B. There are 4. Able to understand? find out these 4 statements, because I want to complete all the theoretical portion today. So next class onwards we can start construction directly. All states of DFA are non-final. Like first one, the one example, right? Other one, you can draw as you like it. You look at all our DFAs. Every state is non-final, then language accepted is pi, empty. And if all states are finals, let's say this is the final and these are also final, second point, it's also final, then every string, what will you do? You will accept it, because for every string we'll alt at final. If every string, if any string that all set final, then we say it is valid string. So here you will have sigma star. Whereas NFA, can you guarantee like this? It's phi only, because if you want to accept something, then you need a final, right? Here the last one is very important. If all states are final, can you guarantee in NFA, which is sigma star? No, right? This is NFA but not a DFA. Is it having every state is the final? Yes. But is it accepting every string? No. Then what is this? We cannot say what is L, but what we can say, definitely epsilon will be there, it is a part of L, but we cannot say what is the language. Okay. If every state is the final, then one thing we can understand, I think, epsilon is there definitely in the language, because initial state is also final. The fourth one, you cannot answer a particular language because you don't know what language that is accepting without looking at it. Okay. And very important points. Now we are going to start construction. I just say model 1. The reason is very easy problems. In model 1, you will see something like language is empty, language is sigma star, language 3 is only epsilon, language 4 is a plus b whole plus. If you want any more, you can do that, okay, on your own. These are one of the easiest problems to start with. Our target is to construct minimum DFA. What is it? Yeah. Let's take these 4 problems to design. First one, pi, and second one, sigma star. Sigma, we are assuming a comma b. And always we design a minimum DFA, as minimum DFA has few number of states and everybody will get the same answer if you follow that technique. Go and design how many states you get. We have already done. Just need to practice more now. How many states you will get to design a DFA? Yeah, everyone should try. Just do something. Later we'll understand how to do it. We want a DFA and we want minimum DFA. Minimum DFA, what is the definition? A DFA which has less number of states compared to any other DFA. This answer for all of you. One. Oh, 3 and 4th, Ishwant. 4th you did right, 3rd you did wrong. Okay. There are two differences, no? Are you designing DFA or NFA? Both are going to be, different approaches, correct? Minimum DFA when you design, you should look at less number of states. That is, you should want empty language to accept. Now, for every input you have a one transition and also there is no final. And this DFA is the shortest DFA in the world to accept empty language. Whereas NFA you want to design, that's it. You don't need to mention for the invalid strings because invalid string never halt at final. Only valid strings with at least one path will halt at final. That strings we wanted. Anyhow, it is one state only. Here also one state that you can remember it or you can write it here itself. You can see. Now sigma star, see these two are complement to each other. And what logic you will apply? You will just make a non-final as a final, final as a non-final. So there is no final here. So every non-final become final. It is also equal to one state. And minimum NFA when you design, should design the same way. There is no other way to accept sigma star. It is also equal to one state. And L is equal to epsilon. Here there is a problem. Initial state must be final to accept epsilon. In DFA, initial state must be final to accept what? Epsilon. After that, you don't want anything. So where do you go if you don't want anything? There is a special state called as a trap. What is this called as? Trap. Once you come here, you will never have a path to the final. So once you come to this state, anybody, they will never have a path to the final. And that's only accepting epsilon here. We don't want any other two. It is two states. And minimum NFA is very interesting. Epsilon, right? Just is it enough? Remaining all, we don't have a path because we don't want to accept them. Here deterministic, even you don't want to accept, you should go to trap state. This is a trap called as. And this one, that's it, one state only. And this one, just complement of this language, right? You have epsilon, you don't have everything else, but you have everything except epsilon. These two are complement each other. In DFA, you can just interchange finals and non-finals. This will guarantee minimum one length, and then you accept everything there. Just final become non-final, non-final become final. But that you should apply only to DFA, not for this. In NFA, you want to accept A plus B whole plus, there are many ways. Now you can put here, that's one way, or you can try, here also you can put A comma B, but it's non-deterministic way. There are many other motions too. But with two states, you can always design any of these motions. Got it? Yeah. So there are a few important points from this. If L contain epsilon, L contains or epsilon belongs to L, then what will you do? Initial state must be final. You cannot leave this. Second, there is a special trap state. It is very special non-final. Right. And why we call trap state, even though it is non-final, there is no path there is no path to reach final state from this trap state. Okay. Once you go to trap state, you will always be there in non-final. It's impossible to reach final by reading any combination after that. No. Now also remember, if you want to do L complement, what is the definition? Sigma star minus L. Sigma star minus L. Like you have L, design a DFA, don't design NFA, correct? And what will you do? Interchange final and non-final. You will get L complement DFA. To get L complement motion. So before designing, these are the very important points. And in the next class, we will start designing a DFA. So by this time, you should know how to understand the DFA. Do you want to try some machines? Okay, model 1, we designed 4 machine set. Before going to model 2, I'll just practice. Okay, I find a language accepted by following machines. Let's see how do you work. Find language accepted by following finite automata. Can try. Next class we will focus on construction. This class understand more about these machines. What is the language? Minimum string is what? B. Next to minimum AB. Next to minimum WAB. And when you look at this, are you able to realize what is the language? B is there, and here AB is there, WAB. So is it looking like A star B only? Is it A power 0B, A power 1B, A power 2B? Sometimes easy to write, not all the times. Remember, don't try all the times to write an expression directly. Sometimes you require algorithms. Don't ever say ending with B. Ending with B in the English language is different. In our language is different. Is it ending with B? No. Is it ending with B? Only some strings. Whenever you say ending with B, this has to come into picture. This will give you every string ending with B. Don't speak ending with B for everyone. Every string it will cover which is going to ends with B. If you want to say ends with B, then A star B looks like ends with B. B star B looks like ends with B. Right? A plus B square B also looks like ends with B. And do you say all of them are ending with B? No. There's the only one which is ending with B that covers every string, and these are only inside it, but they can't cover every string. So do not use the words when you don't understand the definition of the mathematical logic. Is that clear? Ending with B has only one B, that could be the right Sri. Ending with B has only one B, then that can be this one only. Correct. And this one? Here no input is there. When there is no input, what do you mean by it? Epsilon. So language is any number of A's followed by epsilon. What will you get? A star. And here L is equal minimum string. You look at 1A must be minimum. And next one A epsilon A, 2 A's, 3 A's, and which will impact A plus. And this one A star B, B star. You can write directly if you understood the concept. In language, no need to write an expression. You can also write in mathematical notation like A power M, B power N, such that M greater than or equal 0, N equal to 1. You can also write this way. This one. Yeah. Clear? Now I'll give some homework questions. Can you try? Model 2. Model 1 we solved 4 problems, right? You need to construct what? Minimum DFA. At the same time, you can also focus on the minimum NFA. Length based, like length of the string is equal to 2, length of the string maximum 2, length of the string minimum 2, something like that. I'll write expression directly. You will understand. Exactly 2 length. At most 2 length. Remembered? And at least 2 length. What is your job? Design DFA, minimum DFA and minimum NFA possibly. I want you to find out the answers for these 3 problems. In the next class, we'll continue from here. So I want you to try these problems and cover all the basics which is covered so far. Okay. So we'll wind up now and we'll meet in the next session. And as it's the beginning, construction is not important in the beginning class, but from the next class, it's more important for us, constructions. Take it as homework and complete it and come to the next session. Look at how to do them.